All right, so now let's talk about halogenation and hydrohalogenation of alkynes. Just to sort of pick these words apart, halogenation, that's just a halogen, so that would be if I started with something like bromine, Br2, whereas hydrohalogenation, that would be if I started with something like HBr, right, where there's a hydrogen and a halogen that's going to be added. Okay, so let's talk about halogenations first. So the easiest is if we have just an excess of whatever halogen we're talking about. In particular, it actually has to be chlorine or bromine. Iodine doesn't work. But what happens if you have an excess of your halogen, and note that this is, it's called carbon tetrachloride or tetrachloromethane, is just a solvent. Okay, so it's a really good nonpolar solvent that will carry out these reactions. What you're going to get with an excess, right? So here are our two sp hybridized carbons, is you're going to get full halogenation of both of them, right? So now two new halogen bonds have been created. Okay, so this is with an excess of whatever halogen it is, chlorine gas or liquid bromine. But what if you just have a one equivalent here, okay? If this was to our alkenes, we would expect an anti-addition, right? We had, with our alkenes, there was that cyclic bromonium ion that was formed, and so we had an anti-addition. We would expect it to be just the E isomer, right? Or I guess you can't necessarily, can't necessarily 100% conclude it's the E, but bottom line, you have an anti-addition, so the halogens are on opposite sides. It turns out that you actually get, this is indeed the major product, but it turns out that you actually have a minor product, which is going to be that other stereoisomer, the Z stereoisomer, okay? Important to note that the anti-addition is the major product, but the truth is that we do get some of that minor product as well, and the mechanism behind this addition is not that well understood, okay? But you do only have one addition, and I guess let's point out real quick, the key here being your halogens are, in both cases, are added to each one of those carbons, right? So one halogen to one carbon, one halogen to the other carbon. They're not going on to the same carbon, right? So this is with one equivalent. We do stop at an alkene, and that alkene is now a dihalide. And I guess important, it's a sinyl dihalide, right? So they're on opposite carbons. Okay, so in terms of, so these are two halogenation reactions that you want to know. Again, what happens in the presence of excess, or what happens in terms of one equivalent. I'll say that you'll see this written as one EQ halogen, meaning one equivalent of that halogen. Again, what is this carbon tetrachloride doing for you? That's just a solvent. So that's just, you've dissolved these things in this solvent, and that's where the reaction's taking place. So let's just go through our list here, create our little cheat sheet. Do you need to know mechanism? No, because frankly, nobody does. Nobody knows it. It's not very well understood. Maybe there's multiple mechanisms at play, which is why we have this mixture of major and minor. What about regioselectivity? There's no regioselectivity to be worried about because of the fact that we're adding chlorine and chlorine to both carbons. I guess the only caveat would be that you do create the vicinal dihalide, meaning that you're adding a halogen to opposite carbons. They're not both going on to the same carbon. And then is there any stereoselectivity to worry about for this part, for the one equivalent of halogen? you should know that the anti will produce the major product and the syn addition will be the minor product. When you get to the excess, you no longer have to worry about it because you've added 2 halogens to both carbons, right? These are not going to be stereocenters, so not a problem. Okay, so now let's go on to hydrohalogenation. So again, this would be adding something like HBr. As we saw with our alkenes, right? So if we had an alkene and we had, for example, hydrobromic acid, we saw that it was a Markovnikov addition, meaning that the halogen went on the more highly substituted carbon. And that means also, let's just, I guess, to be clear, that means that there is the hydrogen was added to the other carbon, right? We see the same thing with the alkynes. It's again a Markovnikov addition, meaning that the halogen is going to go on the more highly substituted carbon. So again, here we have our more highly substituted carbon that's going to get that halogen. The hydrogen is going to be on the less highly substituted carbon. Okay, so this is what happens when we have one equivalence of our hydrohalogen. So for example, hydrobromic acid, hydrochloric acid. But now what if we have an excess of hydrochloric acid or hydrobromic acid? Notice that we then form the geminal dihalide, meaning that our alkene, or I'm sorry, our halogen is going to, both halogens are going to go onto the more highly substituted carbon. Okay. Yeah, so they're both, so both of these additions, the first addition, as we saw above, will be a Markovnikov, but then you're going to have another round of addition, right? Starting with your alkene product, and that is again going to be added. The halogen's again going to be added to the more highly substituted carbon, giving you this geminal dihalide. Again, gem meaning that it's on the same carbon. So let's talk about mechanism here. So talking about alkenes, our hydrohalogens are strong acids, right? Hydrobromic acid, hydrochloric acid, they're all strong acids. So the first step was this proton transfer, which created a carbocation, and then nucleophilic attack on that carbocation, right? It was this 2-step process. So you might be tempted to think that there's going to be an analogous reaction mechanism for alkynes. This would require, though, the formation of a vinylic carbocation, or a carbocation that's on that vinyl carbon, right? sp2 hybridized carbon. And vinyl carbocations are extremely unstable. So this is not our mechanism. All right, very important. No vinyl carbocations will ever be formed. Okay, not our mechanism. So instead, in order to get like an idea of what the mechanism is behind these, researchers looked at the rate law that corresponds to these particular reactions. And it turns out to be first order with respect to the alkyne, meaning that this exponent, sorry, blanking out there, is a 1. And second order with respect to the halogen, right? So there's a 2 here. So what the heck does that mean? That means that in the reaction mechanism, a collision takes place between 1 molecule of alkyne and 2 molecules of your hydrohalide. Okay, so for example, HBr. So what do I mean by that? Again, 2 of those hydrohalides are involved in that first step. So 1, 2, and then you alkene, that's the third player here. And this is all going to happen all at once. The first step is just like what we saw with our alkenes. What are the pi bonds? What role do they like to play? They can either be nucleophiles or bases. So we have our triple bond reaching up and grabbing this proton here. That breaks that bond there. So this would be a proton transfer. But at the same time, we have our halogen attacking as well. Okay, so both of these steps are happening at the same time. Both of these halogens, 1 and 2, are involved in that first step. So this isn't an intermediate, but rather now a transition state where we have our bonds that are half broken and half formed. Notice that the reason we have a Markovnikov addition, or we have the halogen being added to the more highly substituted carbon, is because this is the most stable transition state, because we have a partial positive charge on the carbon. So we want it to be the most highly substituted carbon, right? That's going to be the most stable. It would be way less stable if that partial positive charge was on this carbon, because it's not as highly substituted. So this is our transition state, and that's how we get our alkene here, okay? Another important thing to note is because of this reaction mechanism, it is an anti-addition. Okay, so this is the hydrogen that was being added. I'll just color code these things to be clear. This is the one that we already had. The halogen is being added from the opposite side of the hydrogen. This is an anti-addition. Okay, that was also sort of illustrated here, just to be clear, right? We have the hydrogen that's added on the opposite side of the halogen. Okay, so now that was if we just have hydrobromic acid, for example. What happens if we have hydrobromic acid in the presence of a peroxide? Do you guys remember what a peroxide was doing for us in the alkenes lecture? Right, so in the presence of peroxide, what we get is on the less highly substituted carbon, or the anti-Markovnikov addition, right? So here, the bromine is being added to that terminal carbon. In the case of hydrobromic acid with, in the presence of peroxide, you actually get a mixture of both the E and Z isomers. We'll call this a racemic mixture, meaning there's not really sort of a preference for one or the other. I would actually expect for this one to be the major product, but just by stability. However, there's not really any evidence for that. Our book doesn't say anything for it, so we're going to assume that a racemic mixture is formed. Okay. Okay. So now again, going back to just the situation with, for example, hydrobromic acid, but again, now talking about an excess of hydrobromic acid, we said that this will form that dihalide, but most important, this is the gem enol dihalide, where both of those halogens are added to the same carbon. So let's see if we can't reason why that is. If we take our one equivalent of HBr, we know that we're going to get substitution on that more highly, we're going to get addition of the halogen to that more highly substituted carbon, right? So in this case, we would get R. Now we have another round of HBr. Well, this is just an alkene. So we actually know the full mechanism for this. This will form a carbocation. Let me actually make room. All right, so now we just have, ignore that as if that bromine wasn't there on that alkene, right? We know what to do here. We have our double bond playing the role of a base, grabbing that proton. This will form a carbocation. And it's going to form a carbocation on the more highly substituted carbon. That bromine stabilizes that carbocation because bromine is relatively electronegative. It itself has this big old electron cloud, and so it can help stabilize that carbocation. So as opposed to it being on the less highly substituted carbon, it's going to be on the more highly substituted carbon. And then what we're going to have is now that bromide ion is going to come along and attack our carbocation. So this is how we have the formation of that geminal dihalide, or where another way of saying that the bromine is on both of those, both of those bromines are on the same carbon when we have the excess of HBr. Okay, and again, that second step, so the first here, this is the reaction mechanism that we just learned that involved both of those HBr molecules at once. I guess I should have pointed out. This is what we call a termolecular process, meaning 3 molecules were involved, right? So 1, 2, 3, this is our termolecular reaction mechanism. That's how we get addition to our alkyne. So that would be the first step here. This is our termolecular reaction mechanism. And then in the second step, this one here, this is addition of HBr to an alkene, which is the carbocation intermediate. Okay, so we actually know the mechanism, the full mechanism for addition in an excess of, for example, hydrochloric acid, hydrobromic acid. Okay, so now, where we were going here, so we have this dihalide. Note that we can also take this, and in the presence of a strong base, what's going to happen? We're going to get right back to our alkyne. Right? So we have a way of going in both directions here, either from alkyne to this dihalide in the presence of excess hydrobromic acid, or we can have our dihalide, and in the presence of a strong base, excess strong base, we'd go back the other direction to our alkyne. Okay, so now just to summarize here, again, always got to know the products that are going to be produced in the reaction. Right? That's step 1. But then we also have these considerations of, for example, mechanism. Okay? In the case of a hydrohalogen, so HBr, HCl, yes, you should know the mechanism for both. I guess to be clear, the difference between these two reactions. These are both just in the presence of some hydrohalogen, but this would be a terminal or an internal. You should know the mechanism, and just one equivalent of your hydrohalogen. You should know the mechanism there. Those are those termolecular reaction mechanisms. Again, fancy way of saying that 3 species are involved. When it comes to in the presence of peroxide, we don't know that mechanism yet. We'll actually get to this in chapter 10 when we start talking about radicals, but we're not there yet. So for now, you don't have to know the mechanism. What about an excess of HBr or any hydrohalogen? Yes. You should know the first step is that termolecular reaction mechanism. And the second, so 1 and then 2, is that carbocation intermediate, just addition to an alkene. Okay? Regioselectivity. Yes, because when we have our hydrohalogen, we have a Markovnikov. Same with the excess of our hydrohalogen. And when we have that peroxide there, the whole shtick about the peroxide is it makes it an anti-Markovnikov addition. Oh, usually that's green. Oh well. Try to keep my color coordination straight. I messed it up this time, whatever. Stereo selectivity. Again, yes, we have, in the case of our hydrohalogen, these are going to be anti-additions. It actually, I guess, doesn't matter if it's a terminal because you don't create any stereocenters. Luckily, in the case of the peroxide, since it's being put on the least highly substituted, you don't have to worry about that. You're going to generate a mixture of the E and Z isomers. And again, we're going to say it's a racemic mixture. There's not any sort of major or minor product. You get a mixture of both. And then when we talk about an excess of our halogen, normally we would have to worry about stereoselectivity, but now we have this geminal dihalide formed. So this is no longer a stereocenter. So this is not no select stereocenter in an excess of HBr. Okay.